we are going to continue with our study today. So today we are going to locate. I think the point is the definition of Riemannian manifold. Right? Yeah. So let me see where I have some space. Yeah, maybe here. Yeah, so maybe let me go over this quickly. I'm going to try to be quick. So, yeah, so what is a Riemannian manifold? So maybe let's say def. Oops. Right, Riemannian manifold. Yeah, so for that I need, let's say an n-dimensional smooth manifold. N-dimensional smooth real manifold. Right, and what do I mean by this? Well, I mean that M has some open cover. I mean, M comes with equipped with a set of charts, right? And the union of the open sets in the charts cover the whole M. And whenever two open sets belonging to charts have non-empty intersection, the transition function that works for the intersection is of class C infinity. Right? So that's what I mean by smooth. Right? If one only requires that the transition functions be, let's say, homeomorphism only, then one has what they call a topological manifold. But then one doesn't have smooth. One doesn't. Yeah, one would have a topological real manifold. Right? If one required that the transition functions be differentiable of class CK, let's say, only up to class CK, one would have an n-dimensional real manifold of class CK. Right? But so smooth is that all the transition functions are infinitely differentiable, first of all. Okay, that's the first thing. And second, one has, so let me go with kind of a bit too abstract, let's say. So together with a function, so together with a function, now let's say a function, and so it's a function g that to each point in M associates an inner product. Right? So what is an inner product is in particular a bilinear form, right? So you can think that it is in particular. So it's a So and then bilinear forms are always in bijection with linear functions going out from the tensor product. So I'm just going to say this Tm tensor product Tm, and I'm going to say some words afterwards. Yeah. So what I mean by this is, you see, is the dual over the real numbers. So what I'm one of the things that I'm saying implicitly is that for each real vector space, there is a bijection between the set of linear functions that go from the tensor product with itself to the real numbers, with the bilinear functions that go from the Cartesian product with itself to the real numbers. Yeah, so kind of one of the things I'm using is this universal property of the tensor product. First. Second, this really, Tm really is the tangent bundle of M. So at least as a set, Tm is the disjoint union over the points in M of the tangent spaces at M, of the tangent spaces of M, right, at each of its points. Yeah, and then at least as a set, and I'm not going to go into how it becomes also a manifold. But the point is that with this bundle, with this tangent bundle, you can take the tangent, you can take the vector bundle, which is the tensor product with itself, which as a set, Tm tensor Tm as a set is the disjoint union of points in M, Tpm tensor with itself, right? Okay, and again, I'm not going to say how is that this actually also becomes a manifold, right? Okay, and then finally, this one is now the vector bundle on M defined as kind of the dual of this one. And so as a vector bundle, as a set, it is the following. So this one is the disjoint union over the points in M of, and then of course now you take this space and then you take the linear maps. So let me do it like this. The linear maps, right? The real linear maps onto the real numbers, right? As a set. So you see this one kind of at each point in M has this dual space to this tensor product, right? And so you see this is what I mean. The elements here are the linear maps from this space to R, but that coincides, or well, that is canonically isomorphic to the set of bilinear maps from Tm cross Tm to R, right? Okay, so I come back here. This function, I require from it two things. One is that it is a section of this bundle, because of course if you describe it this way, one has of course a function from here to M, namely to anything in something here you associate the point at which it's based, right? So this is the kind of the projection to M is obvious, and then what I want, you see, what I really want is that at each point in M I want something that lives in the corresponding tangent plane. So I want this to have the property that composed with the projection gives me the identity of M. Right? So I want it to be a section. Right? And something that I have not said is how this one becomes a smooth manifold. But it becomes a smooth manifold in a natural way, and one requires that this function be smooth. Oops. Smooth. Yeah. And once one has that, then one also requires that for each point in M, the corresponding element here gives you an inner product. So plus for each P, G of P, which I'm going to denote instead of with parentheses, just with a subindex, is an inner product. Is an inner product for the tangent space. Right? So okay, so that's the definition. It's kind of as you can see, it's kind of one has to digest a few things, but my point is the following. checking smoothness usually amounts to the following. Usually, or let's say not usually, but let's say often. When you when you take a point and you represent this one, let's say that you already know that it's at least a bilinear form, right? When you represent it in terms of a basis, and you let the basis somehow vary at least within a chart, that you can do, right? Maybe you cannot let the basis vary in the whole manifold, but in a chart you can. When you let that basis move, the matrix represented this, not the basis, sorry, you let the point move, and hence the basis with it within a chart. The matrix representing this one with respect to that basis, its entries move smoothly, right? So somehow for your question, somehow I'm really kind of skipping all the part that I have that I would have to digest, and then just going directly onto the condition that the entries of the matrix define functions of class C infinity. Yeah, is that, yeah? So. Okay, and now let's go with this group. So last time we already started locating some useful groups. I mean, so useful for studying the Riemannian isometries of the hyperboloid. But then we saw that for example there can be matrices in the Lorentz group that do not preserve the hyperboloid, right? I mean, if you simply think if you think of simply taking a rotation, so let me try and draw. Oops. And then I have my hyperboloid here, well, the upper sheet, right? And then think of rotation around this, which would be the x-axis, right? So let me write. Then, of course, the 180-degree rotation around the x-axis takes me here. And then one can just check that rotation is in the Lorentz group, right? So I would have found what I just said. What I've just done is find a matrix in the Lorentz group that doesn't preserve this upper sheet, right? So somehow the Lorentz group is not quite the group we are looking for. The proper Lorentz group is not either, because the proper Lorentz group is what? Is those matrices in GLR, those matrices in GL3R that preserve Minkowski's form and have determinant 1. Right. So the one I just said also has determinant 1. So okay, so so it's also not the correct one. So, and these ones are going to be the correct groups. So let's define them. So the orthochronous Lorentz group is the you see, kind of I do I define it in the simplest way possible. I mean, I just take all the matrices that do indeed preserve bijectively, that do indeed preserve the hyperboloid, the upper sheet. And then the proper orthochronous Lorentz group, or simply restricted Lorentz group, is, well, I take what I defined, but only those that have determinant 1. Right? Now notice here there are some examples of matrices that don't have determinant 1. So let's see an example, or at least indicate an example. So again, let me draw the upper sheet, and now simply consider the plane. So again, x, y, z. And now consider, let's say, the plane xz. Yeah, so maybe the plane xz, and simply reflect through the plane xz. Reflecting through the plane xz clearly maps the hyperbola, the upper sheet onto itself. Right? It's kind of, yeah. And then you have to check that it really preserves the whole Minkowski's form, and so on. But what I'm seeing is really an explicit example of a matrix that preserves but doesn't have determinant 1. So one shouldn't confuse these two groups. Okay, and somehow the picture that one has to have in mind is this one for the Lorentz group. So we have in the Lorentz group, we have, well, those that have determinant 1, those that do not have determinant 1. Okay, and then among those that have determinant 1, as we have seen, not having determinant 1 does not suffice in order to preserve the upper sheet of the hyperboloid. So we have those that do and those that don't, right? Those that do, but here, okay, I said determinant 1, right? So those that do with determinant 1, and then those that preserve but don't have determinant 1, right? And then those that don't preserve and have determinant -1, right? So it would be something like this reflection that I alluded to here along the xz axis, and then let's say followed by a rotation of 180 degrees. That matrix would live here. Right? Okay, so this is more or less the picture, and of course something that the picture is already suggesting and that would need to be checked is that these are 4 connected components, right? And somehow it's already being suggested that somehow there are no further, let's say, subdivisions there or so on. But that's something that we're going to argue about. Okay, now this observation. So you see, if I take so just something. So you see about notation. The property of preserving M is indicated by writing M as a superscript, right? So somehow, so you see, when I write this, I'm referring to the Lorentz group that doesn't, whose elements do not all preserve M, right? And then when in going from this notation to the other notation, I erase the R and then put M as a superscript. Okay, so kind of just to keep that in mind in order not to get confused. So when I speak here about this is the proper Lorentz group, this is the matrices that preserve Minkowski's form and have determinant 1, but may or may not preserve the upper sheet. Okay, but now Minkowski's hyperboloid is connected. So if I take a matrix and there is some point that under the matrix lands in M, then the whole M lands in M, and this is just by continuity. Okay, so this is very useful, because in order to know that a matrix here preserves the whole upper sheet of the hyperboloid, it suffices to show that it takes 1 point inside, 1 point in the hyperboloid inside the hyperboloid upper sheet. Okay. Yeah, and actually exercise. Can I drop this S? You see, is the observation true also without the S? Exercise. Okay. Yeah, and now I'm going to use this observation to prove that this one acts transitively on M, right? And this one, look, it's not this one. This one is the group of those matrices of determinant 1 that preserve Minkowski's form and preserve the hyperboloid bijectively. This one is only those that preserve Minkowski's form and have determinant 1, but may exchange the two sheets. These ones do not exchange the two sheets. Okay. I'm going to show that it's transitive. So take any point. Yeah. What I'm going to show, let's see. 1 second. Yeah, what I'm going to show is that any point in the hyperboloid is the image under some matrix living in this group of 0, 0, 1. And then somehow the idea is that then this action is transitive because from 0, 0, 1 I can go anywhere, but I can also come from anywhere to 0, 0, 1 via the inverse. So, okay. So take an arbitrary point and take any orthonormal basis of its tangent plane, right? So we know that the tangent plane, we know that Minkowski's form defines an inner product for the tangent plane, and then knowing that, well, of course, I can take an orthonormal basis because I can speak about orthogonality and I can speak about about vectors of length 1. Right? So this notion perfectly makes sense. I pick one such basis, and I'm going to use this fact that we already proved, and then take this matrix. Right? Yeah. So take this matrix. Yeah, and then I'm going to show that it preserves the matrix J, this 1, 1, minus 1, which is the matrix that represents Minkowski's form as a bilinear form from R3 cross R3 to R. Right? Okay, now this matrix, how do I form it? Well, the rows are the entries of this orthonormal basis together with P. Okay. All right, and then I perform the matrix computation, right? So first I do this, and then I get this one. So that's easy, right? Because this is almost the identity, except for a minus 1 here. So the minus 1 goes there, yeah. And then I do this, and then here I use, you see, the fact that this basis is orthonormal for Minkowski's form, right? For Minkowski's inner product. So this one paired with itself, according to Minkowski, is 1. Okay, but this one paired with itself, according to Minkowski, is this times this, this times this, plus this times this, plus this times this. Right? So when I make this product, I get 1. Okay. Also, orthogonality of this one times this one, according to Minkowski, is 0. And so you see, this one times this one, according to Minkowski, is precisely this product, this times this. So I get 0, and so on, right? Okay, this times this it's 0 because this is a tangent vector, and this is p, and so on, right? And so the rest, all of the rest is because just using that this is assumed to be orthonormal, and kind of only remembering that whenever I take inner product, I'm speaking about the inner product coming from Minkowski's form, right? And using this that I know that this any of these two times p using Minkowski's form is 0. Yeah. Okay. And so this means what? This means that I have this equal to this. So my matrix lives in the Lorentz group. Yet this minus 1, it is because I obtain it from this, this times this. The point is p lives in the hyperboloid, and for the hyperboloid is the level set of minus 1.
Yeah.
So this is, yeah. Okay, and so my matrix lives in the Lorentz group. But also notice that when I multiply my matrix with 0, 0, 1, what I obtain is precisely, am I doing it right? So 1 second.
Multiply from the right.
Yeah, so I think, sorry, I should really, sorry, this is a mistake of mine. So this has to be exchanged. Yeah. Yeah, sorry about that, but it really is the same reasoning, and then what one finds is that this one lives in preserves the it lives in the Lorentz group, yeah, and then when I take this matrix, so this would be my matrix A, this one, and multiply it with 0, 0, 1, it gives me, well, ABC, right, which is P. So this matrix preserves Minkowski's form and sends this point of the upper sheet of the hyperboloid to my point that I had taken already. Yeah. So the matrix actually preserves the whole this by the observation, right? I mean, it already takes 1 point. Well, this would be 0, 0, 1, and this would be actually P, right? So it preserves it. Okay, so I'm good. But you see, I'm tempted to say, okay, so I'm done. Now the problem is that A itself may fail to have determinant 1, right? Okay, but what I know, once I'm here, I know that it has determinant 1 or minus 1. Okay. Yeah, okay, so we know that it has determinant 1 or minus 1. But if it has determinant 1, I'm done, right? Because now it preserves, and it takes my point to my point, right? And has determinant 1, so it actually lives here. If it has determinant minus 1, well, from a matrix of determinant minus 1, how can I get a matrix of determinant 1? Well, I can just simply exchange two columns, right? Okay, but then you can say, okay, but changing the columns can mess the image, right? But so you see here you have 0, 0, 1. So exchange any of the two first columns, and you are done. Right. Okay. Yeah, and then in any case, I'm done, right? Okay. So at least this one acts transitively on M. Now, a lemma really kind of from somehow basic topology. If I have a topological group, right, and then I just very quickly remind that a topological group is a group that comes equipped also with a topology and has the property that the product of the group is continuous and the function taking inverses is also continuous. Okay, so if I have a topological group and I have any subgroup, okay, it's equivalent for okay, no, okay. I'm just going to go with a. You see, if the subgroup and the quotient are connected, then the group itself is connected. Okay. And here's the proof. The proof is not hard, and I would say the proof is more or less standard. So I'm not going to go through it, but they are included in the notes, kind of just for completeness. And I'm going to use this lemma to show that the restricted Lorentz group is connected, right? So recall, the restricted Lorentz group is the proper orthochronous Lorentz group. That is the group of 3×3 real matrices of determinant 1 that preserve Minkowski's form and preserve the upper sheet of the hyperboloid bijectively. Okay, so that group is connected. Yeah, and so let's see why. Yeah, so and let's just write G for the group. Yeah, now notice the stabilizer of this one. It's equal to this one, right? I mean, I think it's clear. Should I say something about that? Yeah. So the stabilizer is this, yeah, which is essentially just SO2R. Right. It's essentially SO2R, but you see SO2R is kind of really the circle in disguise. Right. I mean SO2R, it's like 2×2 matrices. 2×2 matrices, I don't know, let's say A, B, C, D. Yeah, okay, like here, alpha, beta, gamma, delta, of determinant 1. But sorry, orthonormal and of determinant 1. Right. So somehow you see this is a vector of length 1. Right? So this is a vector in the circle, and then it being here, it automatically determines the next one, right? Because it has to go counterclockwise. So to determine this, to determine the whole matrix, you only need this piece of information. So you only need the information that lies on the circle, right? So this really is the circle in disguise. Okay, right, but then, yeah, but then being the circle in disguise, it is connected, right? So I have my connected subgroup of G, and now I only have to show that G modulo Gn is connected. Right? G modulo Gn, let's say, only as a set of left cosets. I'm not claiming that this is. I'm not claiming that this is normal in G. Now, the action of G on M is transitive, right? The action of this one on M is transitive. That's what we proved here, right? This is G. Yeah. So the kind of the evaluation function. So you see any element of the group can be sent to the image of, to what it does to n, right? To what it does to n. Yeah. So I consider I consider that function, which kind of I just I think of it as kind of an evaluation function, right? I mean, it's kind of any element of G, I evaluate it at n. Any element, yeah, I just evaluate it at n. It's continuous and it is surjective. That's the point. So it gives rise to a homeomorphism between G modulo the stabilizer of the point and M. Here this should be this other M. Yeah. So this one is homeomorphic to this one, but this one is connected. So this one is connected, and what I obtain is that both the subgroup and the set of cosets are connected. So this one is connected. Okay, and there is an alternative proof. Yeah, kind of just, you see, by now the okay, no, I'm not going to say much more. It's just one can just realize that that this one is diffeomorphic to this quotient. Right? Yeah, so maybe let me just say a few words. So kind of this diffeomorphism kind of comes really from realizing this fact. Yeah, okay, but no, I don't want to say more. Yeah, so the theorem is that the picture that we drew is really more accurate than kind of, you see that it's kind of very accurate for being a picture, right? I mean, it really, this one has 4 connected components, and the 4 connected components are the ones that you are seeing here. So actually, kind of the inaccuracy would be that I should have written this kind of separate. Right? But anyway, yeah, and so the Lorentz group has 4 connected components. The proper Lorentz group, which is this one here, whose elements may fail to preserve the upper sheet, has two connected components. Yeah, and the connected components kind of amount to considering only determinant 1. Right. So I don't think I want to really go on to the proof, but somehow you see the fact that the restricted Lorentz group or proper orthochronous Lorentz group is the connected component of the identity in all cases, comes from the fact that these are all Lie groups of the same dimension, and this one is connected as we just saw, so it has to be the connected component of the identity in all cases. Yeah, and then that you see the kind of this separation really comes from the fact that one can define from the from the Lorentz group a function to a set with 4 elements, which is continuous, and is, you see, just kind of for each matrix you can first consider the determinants, so kind of to separate those that have determinant 1 and -1 first of all. And the second thing you want to do is separate according to whether they preserve the upper sheet or not. So you consider the sign of the third entry of the image of 001 to see whether it's negative or not. Right? And that's how you want to separate. And you see, these really define continuous functions. That's the point. Okay, and like an important proposition, which is, okay, now you are starting to really hit the correct groups, because the orthochronous Lorentz group, the orthochronous Lorentz group is a subgroup of the group of Riemann isometries of the upper sheet of the hyperboloid and the proper orthochronous Lorentz group or restricted Lorentz group is also a subgroup of the group of Riemannian isometries, but its elements actually preserve the orientation. And actually later on we will actually show that here we have equality. Here we have equality, but for the moment we cannot prove it. But actually these are the groups of interest in the hyperboloid model. And somehow the proof is not so hard. Well, the proof is not so hard, except that I'm not going to go into the technical details of what it means to preserve orientation. Okay. I mean, when speaking about what it means to preserve orientation, I'm really just going to wave hands. I'm not going to be very formal. Kind of just for time's sake. Okay. So first of all, consider any matrix. So consider any 3 by 3 matrix. Yeah, and then A as a linear function is multiplication by A, right? So let's say so let me maybe write this very quickly. So let's say alpha, beta, gamma, delta, epsilon, eta, nu, lambda, rho. Let's say that this is A, right? And so AX, the value of A as a linear function of X on a vector X is what is just multiply the vector, right? So it would be like alpha X plus beta Y plus gamma Z, delta X plus epsilon Y plus eta Z, nu X plus lambda Y plus rho Z. Right? So this is when I see A as a function from R3 to R3. Right? Okay, and now what's the derivative? What's the derivative? Well, you take derivative of this with respect to X is just alpha. Derivative of this with respect to X is just delta. Derivative of this with respect to X is just nu. Derivative of this with respect to Y is just beta, just epsilon, just lambda. Derivative of this with respect to Z is just gamma, just eta, just rho. And you see that is just the derivative, which then is a linear map from tangent to tangent, which are again R3 and R3. And so what I'm saying is, when you compute the derivative of the function of the function multiplied by A, and you compute it at any vector, it's again A. Right? Okay, so what advantage does it have? Well, that it preserves, you see, whenever I take a point in the hyperboloid and I take any two tangent vectors, seen as elements of R3, A, since A is here, it preserves the form. Okay. In particular, whenever, sorry, okay, that's true, but I think I need another consideration. Again, if I take any point in the hyperboloid and any vector in R3, any vector in R3, well, A does have this property, right? That A times P, A times any vector in R3, let's say again X, this is equal to the original value because A is in the Lorentz group. Yeah, and so if my vector was orthogonal to P, then its image is orthogonal to the image of P. So this means that really A brings this tangent vector, this tangent space, this tangent plane into the tangent plane itself, right? And here I can think, okay, this is already the derivative, right? So because of this. So what I'm saying is, really one can see this derivative, which a priori is defined in slightly abstract terms, as this very concrete map that you see each tangent vector at P, each tangent vector to M at P, just multiplied with A. And that's precisely the derivative of your map. Okay, and inside each tangent plane, it preserves the inner product, right? Yeah, and so here, yeah, sorry, here really I'm already using, yeah, that A lives in M. That AP lives in M. Yeah, so you see here, for this inclusion, I'm already using that that AP lives in M. Yeah, yeah, and here there's a small mistake. Sorry. Here it shouldn't be this. It shouldn't be this. It should be AP orthogonal to 1. Yeah, sorry about that. Because you see, if X is orthogonal to P, then its image, which lives here, right, is orthogonal to A dot P. Okay, so that's the correct one. Yeah, and when you restrict to the tangent plane, it preserves. So this proves this one, right? Every matrix as a map from M to, you see, every matrix here that preserves M as a map from M to M preserves the inner product. So it's a Riemannian isometry. Okay, and then just that the ones of determinant 1 are the ones that preserve the orientation. It's just, you see, it's kind of one can say, okay, so preserve the orientation, let's say, of R3, right? I mean, they are matrices that are 3 by 3, and then the ones that, let's say, somehow it's clear, intuitively clear what it means, for instance, for the reflection on the xz plane, what it means to change orientation, right? That it changes orientation, and I would say it's more or less clear intuitively what it means that that a matrix of positive determinant preserves the orientation of R3. Right? If we just stick to that notion of orientation, somehow here I would be saying preserving the orientation of R3, if you want. Yeah, and I think for the moment I want to leave it there. For the moment I want to leave it there. Maybe when we see the upper half plane and the Poincaré disk, I'm going to go a bit more. I'm going to go a bit deeper into this orientation preserving property. Yeah. Okay. So now I'm still so right now I'm still interested in studying kind of my study is still focused on the hyperboloid. But I'm going to go quickly to the Poincaré disk, and I'm going to come back because I want to study the shortest curves between points in the hyperboloid, but there is a lemma, or there is a lemma, a result that I don't know how to prove directly in the hyperboloid, and I know how to prove in the Poincaré disk. So I'm just going to go and come back. That also somehow illustrates what happens in practice. That sometimes in some model something is not so easy to prove, so you go to another model. So let's see how to go to the Poincaré disk and how one comes back. And then the point is the following. So consider the point 0, 0, minus 1. So you see, let's say in the unit sphere, we have the north pole, which is 0, 0, 1, and the south pole, which is 0, 0, minus 1. And both are both points obviously lie on the sphere. Now, those two same points, 0, 0, 1 and 0, 0, minus 1, lie on the hyperboloid when we consider both sheets. Right? This one lies precisely in the lower sheet, and then this one lies in the upper sheet. This is 0, 0, 1. So kind of somehow I'm still tempted to say, okay, so I'm still going to call this the north pole, and this is still the south pole, right? Except that now kind of the north pole lies to the south of the whole thing, but okay. Yeah. Anyway, so that's why I denote it by S, and something that I'm going to do is I'm going to place the complex plane as the XY plane sitting at height 0 in R3, and I'm going to project from the south pole between both, right? So from the south pole I throw straight lines, and then I say, okay, so wherever the disk and the upper sheet of the hyperboloid are hit, they are corresponding points under this that I'm again going to call stereographic projections. Okay, so here things are a bit delicate, like, because okay, so how do I know that you see that if I take something very close here, that I'm really not completely out of bounds, right? Or the other way around, how do I know that there isn't some point here in the hyperboloid that really is kind of out of bounds, but the other way here, right? Okay, so one way to deal with this is just come up with a formula, right? And how do you come up with a formula? Well, it's kind of completely analogous of how you come up with a formula in the case of the sphere and C bar, which is, let's say that I have this point here in the unit disk, and I want to see what point in the hyperboloid it corresponds to. So I take, okay, so this let's say this is like something like x plus iy, I don't know, let's say, yeah, and then or the point xy 0, however you want, right? And then you say, okay, I'm looking for a real multiple of it that satisfies the equation something square plus something square minus something square is equal to minus 1, and then you start solving, right? and then you come up with which parameter you have to put that so that it gives you the correct multiple, and then you say, okay, so the formula for this point is forced, and then you check that it's that really is in the hyperboloid, right? And the other way around, right? Now, if you start with, let's say, with this point, it's kind of same thing. You are still looking for a real multiple, but now lying at height 0, right? And then you get your equations, and then you solve them, and then you arrive at these formulas, from the hyperboloid to the unit disk. This is the formula, and from the unit disk to the hyperboloid, this is the formula. You see, what I would say is clear. You see, this is that these are this really give me continuous expressions, right? Here z is always greater or equal than 1 in here. So here, for instance, you never divide by 0. So this is really like super continuous. And something similar here. Okay? Like here you are in the open unit disk, so you really never hit the boundary. So these are really, again, not only continuous but differentiable functions. Right? So these are really homeomorphism. Well, diffeomorphism, I would say. And one checks that they are. One can check that they are mutually inverse by kind of like just checking directly, right? Or kind of, if you came up with the formula, as I said here, kind of by solving the problem of finding the correct real multiple. Then you say, okay, by construction, I constructed this in such a way that they are mutually inverse. Okay, and then some nicer pictures, right? I mean, because this I drew by hand, and this, well, okay, with the aid of the iPad. So you see, this is not a perfect picture. And some nicer pictures that I didn't draw. I took from some other papers, kind of to visualize what goes on, right? Yeah. So for instance, here this curve and this curve, they correspond to each other under the projection from here. Okay, I mean, here you can see this already has, this is very suggestive, right? Of this looks like some sort of circle. This looks like something, right? And then we are going to prove things, right? We're going later on going to prove that this is indeed a segment of a circle and that one has here 90 degrees, but not today. Okay, now exercises. Well, the first exercise is pretty much kind of some steps to actually show that they are diffeomorphisms. So here you have to take the derivative of this. You see, this is a psi. This is a psi. So from the disk to the hyperboloid, right? But somehow thinking that this is kind of a function from a subset of R2 to actually R3, right? And then take the derivative at a point, right? So this is straightforward exercise, and then the upshot is to show that they are mutually inverse diffeomorphisms. Okay, another exercise. Just to check that there may be. You see that. That being bijective of class C infinity does not suffice in order to be a diffeomorphism. Okay, anyway, I'm going to keep going. Yeah, and then I arrive at a redefinition of Poincaré's disk, because first I had introduced the Poincaré disk simply as the unit disk in the complex numbers, or in R2. But somehow that definition was really incomplete. What really is the Poincaré disk is the Poincaré disk as a Riemannian manifold. So it's D together with the Riemannian metric defined by pulling from the hyperboloid to the disk. So you see. Let's say here, let's say that you give me, okay, so this picture is so nice that I don't want to mess much with it, so maybe let me, yeah, and then let me go back. Yeah, okay, so here, so take a point, let's say in the disk. Let's say, yeah, and then So let me choose it differently. So, well, I don't know how to choose it. Okay, so here, so is it kind of so that it doesn't become such a mess, the picture? Okay, so take a point there, and then take the projection to the hyperboloid. So maybe let me try and draw it like, I don't know. Okay, terrible choice of color. Right, and then here downstairs, I have the tangent plane at that point. So let's say this one, and then here let me draw it like this, the tangent plane. Yeah, and then the derivative of the projection takes this tangent plane onto the tangent plane at the hyperboloid, to the hyperboloid at the image. Right? So, and that's what is going to be really hard to draw. Yeah, okay. So the derivative takes this tangent plane, which is canonically identified with R2, to this tangent plane, right, which is the Minkowski orthogonal to the point. Okay, and here we have an inner product defined. So something that I can do to define an inner product here, which is not what I already knew from Euclidean geometry, which is okay, just the usual inner product, not that. Another thing I can do is, if you want to define the dot product of two vectors here, okay, map them here where you have something, where you can pair them with an inner product, and define the inner product of these two guys just to be the inner product between their images. That's exactly what this formula says. So define the inner product of two vectors, of two tangent vectors at a point W to be Minkowski's pairing between their images. What are their images? Is their images under the derivative of C. That's what we do. And then here you see here I'm using kind of this notation that somehow kind of I introduced earlier, right? Okay. Yeah. Right, and I'm saying the Poincare disk is this, where this is the Riemannian metric defined by blah blah. The point is that here somehow I'm already tacitly using that I know that C is a diffeomorphism. So being a diffeomorphism, whenever I have a Riemannian metric here and I do what I did, what I obtain is a Riemannian metric. In other words, if I pull a Riemannian metric along a diffeomorphism, what I obtain is a Riemannian metric. Okay. Of course, now I have a nice formula for computing the inner product if I'm in the hyperboloid, and I would like a formula, an explicit formula, to compute when I am in the disk and I want, let's say I want to stay in the disk. I don't want to always have to go to the hyperboloid in order to be able to compute an inner product. So that's what I do. So first I notice that since the disk is contained in R2, for any point I can identify the tangent plane canonically with R2 via just the partial derivatives, right? And it's kind of the actual, you see, for any point, the identification is, well, you see, seeing this tangent plane abstractly, kind of as the set of the space of derivations of blah blah that satisfy the Leibniz rule. So any such derivation, yeah, I don't want to go too much into you see, this, let's say the partial derivative with respect to x gets identified with 1, 0. The partial derivative with respect to y gets identified with 0, 1. Where somehow here I'm seeing things according to the local chart D itself. All right. Now the point is that it is possible to canonically identify any of these tangent planes with R2, and when with that identification, you see this when one makes this computation, that computation gives you this formula, where here u and v are tangent vectors, and you see here this, you see, let's say u is equal to u1 u2 and v is equal to v1 v2, and here you have the usual dot product, but that dot product is rescaled according to according to w. So here somehow you see this somehow tells you the following. Let me draw. Oops. Let me draw the unit disk. Right, so this is D. This is D, and let me take a point W. Right, so here is my point W. And then I draw the tangent plane, which is canonically identified with R2, but somehow I draw it as if it were anchored in W. And then I take my two vectors, with same color, my two tangent vectors, right, for which I want to know the formula. Right? And somehow this gives you something funny. So somehow it's the usual Euclidean product, but if you let your W vary, if you let your W move, when it starts getting close to the unit circle, this becomes very big. This becomes very small. So this becomes very big. So this becomes very big. So let's say if both vectors are the same, and then you are really speaking about the square of the norm. Right? It tells you somehow it's the Euclidean norm, except that when it's close to the unit circle, it becomes arbitrarily large. Right? So somehow this same vector that I'm drawing, if I move it around, and I move it around in the disk, kind of already using the fact that any of these tangent planes is identified with R2, right? Kind of this kind of very same vector, close to the disk, close to the circle, it's super big, and close to the origin, it's something very close to its Euclidean size, right? In other words, when I stand close Euclideanly to the unit circle, things become very large, and close to the center, things are kind of close to being to the Euclidean sizes. Okay, and then just to finish for today, I just want to say that somehow one usually just goes to a book and then it just gives you this formula, and somehow, okay, I mean, one can make sense of, okay, this is the usual dot product, and then kind of you rescale it in such a way that this that I just said happens when you are close to the unit circle. Yeah, but somehow is, why on earth would you come up with this, right? I mean, okay, forget about the 4, right? Let's say whatever constant, but how, or like, why this and not, and with, why only 1 square? Why 2 and not 1? You see, I mean, okay, and the way I see it, you see, how one comes up with it is just, okay, no, just when defining Minkowski's form, you just change one sign, right? And so things are really natural, I would say. Okay, and that's it for today.